So today I will recall a few properties of the characters of representations of finite groups, and I will then examine some examples using two theorems about characters, which will be proved in one of the next lectures. So you see, before seeing the proof, you can see the meaning and the significance of these two theorems. Okay. So where are we? If we have, if G is a finite group, we know that a representation R is a homomorphism from G to GL of V, where V is a vector space over C. Finite dimensional vector space over C. Okay. So in one of the last lectures, the character of a representation was defined. So the character of V is a function from G to C, and by definition, the character of an element of V, of an element sigma of G, is the trace of A sigma, where A sigma is just any representative matrix of sigma in GLV. Now, whenever you fix a basis in V, you have a representative matrix for sigma. So you compute the trace. So A sigma in GLV is any representative matrix of sigma. So by definition, we see that just by its definition, we see that chi of V of sigma is well defined, because recall that any two representative matrices of an element sigma are conjugated in GLV, so they have the same trace, right? And another property is that for every G in G, chi V of G sigma G minus 1 is equal to chi V of sigma. What does this mean? This means that this function is constant on conjugacy classes of G. So, chi is V is constant on the conjugacy classes of G. If we want to check this, we can check it. So we have that chi V of G sigma G minus 1 is exactly the trace of the representative matrix, of any representative matrix of the element A, G, sigma, G minus 1. But recall that R is a homomorphism. So this matrix is just the product AG, A sigma, AG minus 1. So you see, again, you take the trace of two conjugate matrices, so you get the same number. So then we say that chi of V is an element of the so-called central functions on G or class functions on G. The two names which mean the same thing, which is that they are constant on conjugacy classes. And this is a subset of all maps from G to C. But these one are constant on conjugacy classes. So they are called either class functions or central functions on G. Now we want to point out that these functions are in fact a subvector space of all functions from G to C, and their dimension is equal to the number of conjugacy classes in G. So it's a fact. It's CG is a subspace, a vector subspace of these maps of dimension, and the dimension of CG is equal to M, where M is by definition the cardinality of the set of conjugacy classes of G. Okay, the fact that these maps form a vector subspace is not so difficult if you think, right? Let's prove it. So if we take two functions, f and g, which are in CG, we want just to show that a times f plus b times g on sigma are constant on conjugacy classes, but by definition, this is a and b are complex numbers. We are just saying if you take the value of this function on sigma is just a times f of sigma plus b times g of sigma. So now it's clear that if f is constant on conjugacy classes and g is, the same is true for any linear combination of them, right? Maybe you don't see well here, but this is equal to, by definition, this is equal to a times f of sigma plus b times g of sigma. So, okay? For the second point, again, if we take functions, suppose that we number the conjugacy classes, sigma 1, sigma m, the conjugacy classes. We can always construct a function which is which value has value 1 on a fixed conjugacy class and 0 everywhere else. So these functions are clearly linearly independent, and they span CG of C. No? For as like the now, if I take fj of sigma k equal to delta jk, this certainly is a function in CG. No? Means that the value of fj is 1 on the j conjugacy class and 0 everywhere else. These clearly are M independent functions. Is it clear? So we have that central functions are a subvector space of these maps of dimension equal to the cardinality of the set of conjugacy classes of G. Now, in general, the number of conjugacy classes in a group is less or equal than the cardinality of the group. It is equal when the group is abelian, if and only if, in fact, right? So. Another observation which we can do about characters, simple observation, is that another observation is if we have that V is a representation And suppose that V decomposes in the direct sum of two representations. So V is equal to V1 direct sum V2. So VI G representations. Then we can say that the character of V is equal to the sum of the characters chi of V1 and chi of V2, right? Why is this? Well, if we have the vector space V, we can always choose a basis of V which consists of a basis of V1 and a basis of V2, no? Two disjoint sets. And then any representative, no, if I take a basis of V, no, take a basis of V equal to like a basis of V1 union a basis of V2. Then any representative matrix for the representation V is block diagonal. No? So if I have A sigma for V, will be something like A1 sigma 0 0 A2 sigma. No? This is, and so the trace of A sigma will be the sum of the traces of the two components. Okay. And another observation we can do is that if we have the trivial representation, then the character of the trivial representation on a vector space of dimension n, what is it? If I have V and G acting trivially on V, then the character is identically equal to the dimension of V, right? Agree? So now I will write here on the blackboard two theorems about characters, which will be proved by René. And so I write them so we have them, and we explore them in some examples. So this is what René called Theorem 3. If you have, G is the same finite group, no, fixed. So if V1 and V2 are isomorphic representations, if and only if the two characters, the respective characters, are the same as functions on V and functions on G, sorry. And Theorem 4 says that if you have the set of characters of G, where V is irreducible, then this set of functions form an orthonormal basis of the space CG of class functions, where here orthonormal means with respect to the inner product that was defined last lecture on the functions on V. Where if we have chi V1, chi V2 was defined as 1 over n. N is the cardinality of G. Sum for sigma in G, chi V1 of sigma, here V1, V2, chi V2 of sigma complex conjugate with respect to this Hermitian product on the functions. Two immediate consequences of this theorem is that if you have a finite group with m conjugacy classes, then it has exactly m irreducible, non-isomorphic representations. So, consequence 1, G with m conjugacy classes, G finite, of course, and then there are precisely m irreducible, non-equivalent representations of G. And two irreducible representations are distinguished by their characters. No? If we have two representations, we can check their characters. If they are equal, they are equivalent, otherwise not. That's it. So, two irreducible representations are non-isomorphic, are isomorphic if and only if, but I said it already, are non-isomorphic if have different characters. Of course, first of all is the dimension representation, is the first invariant that you can think of, but suppose that you have two representations of the same dimension, no? Where they act irreducibly on a vector space of the same dimension, then you want to know whether they are equivalent or not. And then you check the character. Okay, so the first example that we will consider is the cyclic group Z mod 3. But before doing that, we observe one thing, is that if we have an abelian group, no, a finite abelian group, then every irreducible representation is one-dimensional. Okay. So, the wrong blackboard where to write the theorem. Okay, so suppose now we do the following lemma, let's say, lemma or fact, whatever. Lemma, if G is finite abelian, then, and V is irreducible representation, then the dimension of V is 1. It's a short proof, so we do it. And what are we going to show? We are going to show that every element of G acts on V by scalar multiplication. Proof. We show that every sigma G acts on V by scalar multiplication. Okay. Is it clear that this implies the theorem? Why it implies the theorem? Because like every element acts by scalar multiplication. What does it mean? It means that rho sigma of V is lambda V for some lambda depending on sigma. Oh, we are going to show this. If this is true, then by irreducibility, the space has to be one-dimensional, no? Because every line is sent into itself by the elements of the group. So if you want it to be reducible, it has to be a line. So this is for every V for some lambda and for every V in V. Okay. So what do? Now we take an element, sigma, in G, and sigma acts on a complex vector space, so it has at least one eigenvector. So let V in V a non-zero vector such that sigma of V is lambda V. Okay. Now we show that, so this means that this vector V sits in the lambda eigenspace of sigma, right? Okay, now let's look what sigma does on GV for every G in G. Now, okay, maybe I erase the consequences here, otherwise I don't know where to write. Okay. Okay, so I take sigma. I take now, I compute sigma of GV. Since G and sigma commute, G is abelian, this is G sigma V, and sigma V is lambda V. So this is G lambda V, but this is a scalar, so crosses over G, so this is lambda GV. So this expression shows that, in fact, the eigenspace of the lambda eigenspace is actually preserved by all elements of G. No? This shows that G of V lambda is sent into V lambda. So it means that V lambda is a G invariant subspace of V. And then by reducibility, it has to coincide with V. And so, hence, by irreducibility. So this, we can repeat this argument for every sigma in G. So it means that every element of G acts by scalar multiplication on V. So V has to be one-dimensional. Okay. So now the first example we do is exactly Z mod, G is the abelian cyclic group Z mod 3. So G mod 3. So it's abelian, it's cyclic. So, and how many, so the cardinality of G is 3, is exactly equal to the number of conjugacy classes. So by the theorems and the lemma, we know that there are 3 non-equivalent representations of G. Irreducible, they are one-dimensional, they are already irreducible, no? So we have to construct, so there are 3 non-isomorphic irreducible, they are one-dimensional representations of G. Okay, so we call them rho 1, rho 2, and rho 3, and we are going to write the character tables, the character table for these representations. Well, in this special case, since the representations are all one-dimensional, they coincide with the character. No? If you take a one-by-one matrix, the character is the matrix itself, right? So here we write the 3 conjugacy classes of G, which is 1, W, and W squared. Of course, W is a generator of G. So W cube is equal to the identity. And then we have here the 3 representations. And here we will write the characters on the elements. So we have rho 1, rho 2, and rho 3. But 1 is the identity. Every group has the trivial representation, right? So the character is 1 on each element. For the other 2 representations, we can have, we can just say, okay, maybe rho 2 is, rho 2 of W is Z, where Z is a complex number such that Z cube is equal to 1, precisely, okay, Z cube, for example, see, we can take e to the pi I over 3. It is enough that we know the representation on a generator, no? Because later we know what, so rho 2, and then we have rho 3 of W. We take the square of this element. So what does this mean? So rho 2, we said in one-dimensional case it coincides with the character. So the character at 1, the character is always 1. On W, we just said that it is psi. And on W square is the square of psi, so psi square, or Z square, I don't know. Z square. And for rho 3, we said that the character of the identity is 1. Now, on W, its value is the square. And on W square, it will be the square of the square. No? So here will be psi square square, which is, you know that psi to the cube has to be 1. So here it remains psi. See? So this is the complete character table. And from this table, we can see, for example, that these 3 representations are not equivalent. You see, the 3 characters are different, at least on the generator of the group. So you see that rho 1 or W is different and this says that the rho 1, rho 2, rho 3 are non-isomorphic. Non-isomorphic. By irreducibility, we believe it. But for curiosity, we could compute the norm of these three characters. For example, if I compute the norm of this character, what do I get? I get psi 2 against psi 2, it is 1 over 3, and then 1 square plus psi bar, so the absolute value of psi square plus the absolute value of square of psi square. So these are roots of 1. So this is exactly 1/3 times 3 is 1. Right? And you can, and the same holds for this. You see, the norm square of chi 2 is the same as the one of chi 3. Oh, so this is also equal to chi 3. So if we really want to go a bit further, we can also check that indeed the characters of chi 2 and chi 3 are orthogonal with respect to the norm that I wrote earlier. Or maybe you can do it as an exercise, and I go to S3. Aspetta. So, okay, check that, for example, psi 2, psi 3 is 0. But in fact, if you do the computation, this is 1/3, 1 plus psi square, psi bar square plus psi square psi bar. And if you compute this, you get 1/3, 1 plus, you say here what you get is psi bar, no? Psi bar goes away, and then here it remains psi. So this is 2 times the real part of this primitive cubed root of unity, which is -1/2. So this is -1/2. So here you get 0. Okay? So that you get 0. Now we go to the next group, which is not abelian, and in S3. S3, we already know something about S3 and its representations. Maybe I erase the statement because this blackboard is better. I have another 15 minutes, right? Yes. Till 10 to. Okay, okay. No, I have time. So now we take. So is it clear the example Z3? Okay. So now I take G is equal to the symmetric group in 3 elements. And wait, let me take the matrices. Okay. So the cardinality of the group this time is 6, the number of conjugacy classes is 3. You remember, conjugacy class is the identity, the 2 cycles, the 3 cycles. And of this group, we know already a few representations. So it means that this says that there are precisely 3 irreducible representations of G which are non-equivalent. So we know the identity, we know the sign, and we know, remember the representation, the action of S3 on V0, this plane in C3 where sum of the coordinates is 0. So we know we have row 1, the trivial representation. We have row 2 of sigma, the sign of sigma. And then we have row 3 from S3 to GL of V0, where V0 is the plane in C3, Z1 plus Z2 plus Z3 equal to 0. You remember? No? The action of S3 permutes the basis vectors of C3, and C3 can be written as V0 plus the span of 1, 1, 1. You saw it in the lecture, you remember. So here S3 acts as the identity, because if a vector has all the coordinates the same, this action does nothing to the vector, while here it acts, but this has dimension 2. And so now we try to write the character table for S3. So here we have the equivalence class of 1. Here we have the equivalence class of the 2 cycles, and there are 3 of them. This conjugacy class has 3 elements, and then we have 2 elements in the 3 cycles. Okay, and then we have, now we write the character Chi1, characters Chi2, and Chi3. Okay, 1 is the usual one. 1, 1, 1. Chi2 is one-dimensional, so the trace of identity is 1. The sign of the transposition is -1. And the sign of 3 cycle is 1. No, this is even. And now what do we know about Chi3? We know that this representation is 2-dimensional. Now we go a little bit backwards. We write the character of the representation row 3, and then we check that has norm 1. So this already implies that the representation is irreducible, and then we compare it with the other ones. Okay? So Chi3 of the identity of 1 is 2. Now we want to compute Chi3 on the 2 of the transposition and on 3 cycles. So Chi3 of, for instance, 1, 2. We can check 1, 2 because it's constant on conjugacy classes. So this is the trace of the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1, minus, we have to remove the contribution of this component. No? Now we do, I compute the trace of the 3 by 3 matrices. Notice that this is dimension 2. So I have to remove the contribution of this copy of the identity. So -1 to put here, -1. So this is 0. And if I do on a 3 cycles, in a 3 cycle, 1, 2, 3, for instance, I have to compute the trace of 0, 1, 0, 0, 0, 1, 1, 0, 0. Again, -1, I have to remove the contribution of this trivial component. And what do I get here is -1. So I complete the character table. On the transposition is 0. And on 3 cycles is -1. Maybe, you know, you could always ask, but why don't I use 2 by 2 matrices, right? You could also ask that. Oh no, you have to fix a basis of V0 and check what the representative matrix is there. For instance, you can just, if you take as a basis of V0, for instance, the 2 vectors, 1, -1, 0, and 0, 1, -1, in this basis, the matrix of 1, 2 would be -1, 1, 0, 1. And the matrix of 1, 2, 3, row 3, sorry, row 3 of 1, 2, 3 would be a 2 by 2 matrix, 0, -1, 1, -1. Now, these 2 by 2 matrices have the right trace, right? You see, this has trace 0 and this has trace -1. But they are not so elegant, and especially if you want to generalize your arguments to Sn with n larger, it is nicer to reason on the space C3 and then remove this contribution from the trivial component. Anyway, so we have the character table. So now let's check that this is irreducible, computing the norm of chi3. So now claim row 3 is irreducible. Suppose that René did it geometrically, no? But suppose that we just want to check it using the character theory, the character properties. Check that, in fact, I can do chi3 is equal to 1/6, and now I have to do 2 square plus 0 square 3 times 0 square plus 2 times -1 square. So you see what you get. This is a 1/6, 1/6, 4 plus 2. You see? Is 1. Of course, Psi3 as dimension 2, Psi2 and Psi1 as have dimension 1 is obviously they are not equivalent, right? But the fact that all these 3 representations are non-equivalent, you can also see it here, you see? On the 2 cycles, these 3 characters take a different value. So the representations are non-equivalent. But if for curiosity we want to compute, for instance, it's clear that the norm square of chi1 is equal to the norm square of chi2, and it is equal to 1. No? For instance, let's check that these two are orthogonal for this norm. And, or actually, let's do Xi1 and Xi2, for example. That is less obvious that are non-equivalent. So, no, this because the three values, but what if I compute now, for instance, Chi1 and Chi2, the inner product? It is just to illustrate the theorem. No? Here we are not discovering anything new in this moment. No, it is, okay, but it is just to check. So it's 1/6. So 1 plus 1 times 1 square plus 3 times this, so -1, plus 2 times this times this, which is 1. So you see you get 0. So you see, here to do this computation, not only we needed the number of conjugacy classes that determines the number of non-isomorphic representations, but to check these orthogonality relations, we also need the cardinality of all the conjugacy classes, you see? If we do Xi2, Chi3, again, it's 1/6, 1 times 2 plus 3 times -1 times 0 plus 2 times 1 times -1. So 2 minus 2, 0, you see? 0, as we expected, but it is just to check it. Okay, so maybe next group would be A4. No, maybe I just start and then tomorrow we finish. For instance, just 2 things I want to say about A4, because I cannot finish it now. A4 has how many elements? 12. How many conjugacy classes? 4. Remember? So we expect 4 irreducible, non-equivalent, non-isomorphic representations. So 4 irreducible, non-isomorphic representations. So 2 we get for free almost. 1 is the identity, no? So rho 1 is equal to the identity. Another one, we can actually deduce it from the permutation representation of S4. No? A4 is a subgroup of S4. So we take rho 2 is equal the permutations representation on C4. You know that this is not irreducible, not even by already by S4, but on we take V0, the set of vectors in C4, Z1 plus Z2 plus Z3 plus Z4 equal to 0. This is 3-dimensional. For instance, suppose that we want to know whether this representation remains irreducible when we restrict it to A4. What do we do? we have to compute the character. If the character has norm square 1, then we can conclude it. Okay, so the claim is this is irreducible. But then we need 2 more. And to construct 2 more, we need some more work. And we do it tomorrow. But already to check that this is, maybe try to think how to do, how to compute the characters. And then, of course, we do it together tomorrow. Okay? I think it's, yeah.